And let's think about this. You have a deck of cards in the first problem. We all agree on the first problem. Is that correct? Nobody has a problem with the first problem? Okay, so you have a deck of cards, and in the deck of cards there's 52 cards. Of those 52 cards in a deck, this is without jokers, right? You know that 1/4 of these 52 cards are spades, 1/4 diamonds, 1/4 hearts, 1/4 clubs. Everybody okay with that? All right. So we know we're going to have about, if you have a total of 1,600 cards, then what you would expect to see is 400 of each suit. That's your expected in a regular deck of playing cards. All right. So now, what if you didn't take the jokers out? There's 2 jokers in every deck. So instead of 52, you'd have 54 cards, right? And I tell you that we had these, we filled up our dealing machine with 1,662. 1,662. Well, how do we find out how many jokers are in this 662? Well, we need to know how many 54s there are in 1,662. How many 54s are there in 1,662? In other words, how many decks do I have in 1,662? A little bit. What's the exact number? 30.777. So 30.777, and if we round up, it would be 31. So it's approximately equal to 31. Do you all agree on that? So it's 31 decks. So 662 gives you 31 decks with the jokers in it. So the 31 times how many jokers per deck? 2 jokers, the big and the little, right? So we got 2 jokers per deck. So that's 62 jokers is what we would expect to have in 662 cards. Yes? Huh?
This is what I was saying earlier. The first one is without the jokers. So just subtract different ones that have the jokers and see how many jokers were added into it. Subtract the first one.
Yes, I understand I understood what you were saying initially as well, but to subtract that would imply something that's not stated in the problem. Okay. Does that make sense? They didn't tell. Say what?
That makes sense.
Okay, so they didn't state that they kept the problem the same. But it's good that we see that the 2 problems are related. Now we know that they're related. So we have 62 cards, 62 jokers. And do you see what she's saying? Do you see that in the first problem we had 1,600 and now we have 662? And that's what earlier she mentioned that if you subtract the 2, that's how many extra cards you have, that's how many jokers you have. But we didn't know that in the problem because it wasn't stated. But now by figuring it out, by doing some math and some thinking on our own, we found out that actually it was exactly what she said, which is those 62, those extra 62 that you see here were the jokers that were added to the deck. Are we all clear on that? Mm-hmm. Okay. So we have 62 jokers. So then, if we do the math and we ask ourselves, well, we don't have to do any more math since now we know that there's 62 jokers. That means there's 1,600 other cards, right? 1,600 other cards. And there's 4 different kinds, what do they call these things? Suits. So there's 400 each, right? Just like the first part of the problem. So now you know you're expected again, don't you? 400 for each suit, except the jokers, which you expect to see 62. You see in the problem set, let's go back to the problem set, here, and you see right here in the problem set that you have your expected, your observed, and you have spades, hearts, diamonds, clubs, jokers, and then your total. So you should be able to do that, yeah? You can fill out the chart. Does everybody see how to read a chart like this? Okay. right, so I think you can do the problems now. You may not get them right, but we're going to go over some basics in a second. For this as well, just a quick review. Remember that chi squared, which is funky looking x, right, squared. It's not actually a variable. It's a term. But chi squared is the sum of, right? Do you remember that? And the sum, that's what this letter means. The sum of, right? This is another Greek letter. The sum of what? Observed minus expected squared divided by expected. All right, so what would those be? What is it that we need to add up? Well, let's do it. Let's go over it, and then I'll let you do the rest of this at home.
So how do we know if our numbers are too big and so they aren't random or not big enough that it disproves our observed?
Right, how do we know? So let's go through that. When we are looking at a distribution, and that could go for anything, right? Number of heads, number of tails, it could be how many A's, B's, and C's we have on a test, right? On average, if there's nothing else going on, life is, if it's just random, this is what you're gonna get. A bell curve, right? More or less. Let me redraw that. You're going to get a bell curve. So what's the likelihood, do you think, of people, of whatever it is, whatever you're looking at in the distribution, that it's going to be here in this area or here in this area versus the middle portion? Just looking at the area. Forget the word average. What is it for? Okay, you're saying 50%. That's good that you're making a guess at percentages. But look at this graph. Look at this area. There's a lot of area here. What are the odds you're going to get? Let's just say this is 70%. This is 70% here, right? What are the odds, and this is grades, these are grades. What are the odds that you're going to get 70%? If this is a distribution of grades in the class, it falls into a bell curve, what are the odds that you got 70% on the test? Pretty good, right? It's high. Because look, if these green dots are your scores, these are your scores. Each one of these green dots represents one of you guys, okay? Most of the green dots are where? In the middle, right? Right here, somewhere in the middle. That's what we call an average, right? Somewhere in the middle. Not the highest, not the lowest, not the exact middle. The exact middle is not called median. The average is somewhere that you fall within a range. We call that an average. What are the odds that you would fall all the way over here? Very small, right? What are the odds you'd fall over here? Small. So it's highly likely that you fall right here. So what does this 0.5, etc. mean? Well, let's take a look at the picture that represents that. Here's a picture, critical value. Here's your critical value. Those of you that could not answer me as to what critical value is. Let's take a look at it. And let's take a look at the same idea with numbers. All right, let's take a look at the same idea with numbers. All right, so do you agree that all three of these have basically the same shape? Do you see why we call it a bell curve? Okay. If you fall in this area here, if you're not, this is kind of where we would randomly say, if you're within this area, right, then your null hypothesis, we're going to accept the null hypothesis or reject the hypothesis, right? So what we're saying is that if it falls around here, now what is this? This would be what? Your predicted value, your expected value, right? Whatever this is your expected value. Do you see that? This is what you would expect to see. Now, could you get a number that's over here? Sure. So this would be, in the case of flipping the coin, that would be what? 50%. So could you get 40%? Sure. Could you get 60%? Sure, that's reasonable. right? But is it likely that you'll get 95% or just 1% heads? I'm going to reject that. I'm going to say it's not by chance. I'm going to say something else is going on. If it falls in the blue area in the case of this diagram, that's where we say it's not, we're going to reject it. Does that make sense to you? So this value, this line, this it's arbitrary, isn't it? How much where do I draw that line? Do I draw this line here? Do I reject it here? Or do I wait all the way over here to reject it? Do I draw it here, or do I draw it all the way over here? You know what I'm saying? Where do I draw that line?
And that's what the degree of freedom is.
No, that's what the critical value is. What percent? That's what that 0.05.
Where you decide where you stop.
That's critical value. Yeah.
So
Like that 0.05. Let me switch back for a second. Okay.
Okay, so you're saying that where do I stop it? Do I stop it there or there?
Right. Well,
That's decided
by critical value.
by the
That's what the critical. See, that's what the critical value is, right? So let's take a look at this. Sorry, I had to get my medicine in me.
So you decide
See this?
to stop.
You decide where to. That's right. You as a scientist decide.
You decide that based on what you got for the degree of freedom. So that
No.
was the
No. Good question. Good question. I mean, it really is a great question. It's showing thinking. You see how she's thinking about it? No, degrees of freedom is something slightly different. In fact, we'll leave that for another day, because we're running out of time. But right now, how do you decide what your significance level is? That's what we're talking about. Critical value, significance level, or if you're doing a p-test, if you're doing, you can call it critical value, whatever, all right? Forget these labels. I don't want you getting confused. Because there's all kinds of statistical tests that you can use, okay? And when you get in AP biology, you'll get more into this. But let's go into the idea that, let's just look at this in general, okay? That if it's significant, if it's due to the difference from the expected value, again, where's the expected value? Right here, right in the middle, right? That's what we expect to see. If we expect to see this, but instead we see something over here or over here, we're going to say it's probably due to random luck, right? Because that's possible. It's still within the... And how do you decide that? Well, you decide that because you know something about your subject area. You know something about the probability of something happening. You have some idea. That's where your scientific mind comes into play. Where you draw this line, you see, look at the percentages. Look at what they got. Look at the numbers. 0.05. That's if they use 0.1, then that would be 0.1 is all the way over here.
Yeah, and that's what they use in that picture. On that bell curve.
On the other one,
No, on that one.
on this one. They're saying any one of these. They're telling you, if you look at the chart, and I don't want to flip back to the previous screen, but you saw that it was 0.1, 0.05, 0.025, 0.01, 0.001. All these are here.
Okay.
And the reason that they're here, and you don't even see 0.001, in places where you have devices that can measure very accurately, and you can get rid of a lot of errors, a lot of sources, they're very controlled experiments, then you would say, you know what, I think it should be 0.001, anything within, I'm sorry, we should have this space very, very tight. Does that make sense? So if this is the expected value, I'm so sure about the way I measure it, and I'm so sure about everything that's going on, because I'm the scientist, I know what's going on, right? I have some idea, I've done some research. I think it should be somewhere around here if my hypothesis is correct. Anything outside of this area, there's something wrong. If this is 10%, no, I was right the first time. 80% of the data is here in this yellow area if I'm using this critical value. Because 10% is too high and 10% is too low, the Goldilocks range is here at 80%. So there, if I'm more sure that my data, what my results should be, if I'm very sure about my hypothesis, then I'm going to say if it's anything outside of that 80% range, I gotta kick it out. But if I'm not so sure, then I'm gonna reduce that critical value to 0.05. So what does that mean? That means that now, if it's within 95% of the total data, then I'm gonna go ahead and accept it. I'm gonna say that any difference from this value is due to random luck. Did I mess that up? Yes, it would be 90. Thank you. Sorry about that. Yes, 90. So at 90%. Does that make sense to you? Because then this is our critical value. 0.05 plus 0.05 is 0.1, which is 10%, leaving you 90% of the possible measurements with inside possible scores or measurements, observed data within this yellow area. If I'm really, really, really super sure, I can take it down to 0.001%, 0.001%. That means that, what does that mean? That means that anything what that means is that anything I measure that's not the extreme values, right? Then I'm going to accept the null hypothesis and say any difference from my measurement is due to random luck. It's rare that we would use 0.001. With a one number that most people that you'll see, and I don't care if you're going to be a business major, you have to do this. You'll have to do this if you're a history major. You have to do this if you're a biology major. Statistics is going to be required. The only people that probably don't use statistics are people that are actual writers. But even publishers have to use statistics. So you have to be familiar with this. Everybody takes statistics in college nowadays. Is the value that we generally use when we're looking at critical values. So anything that above 0.05, right? When the critical value is when that number that he's gonna talk about in a minute, if that number ends up over here or ends up over here, anywhere beyond this line, right? Beyond this green line, let's use red line. Anything beyond this red line here, we're gonna say that we're going to reject the null hypothesis. What does rejecting the null hypothesis mean? It's not due to luck. It's not due to luck. The null hypothesis means it's due to luck. Right? The null hypothesis means that anything you measure that does not fit anything that's outside the difference between the observed and the expected, that's less than this critical value, in this case what? 5% too high or 5% too low, if it's within that 90%, then it's any difference from your expected value is due to luck. So if I see 60 instead of 50, right? Then I'm going to say it's due to luck because that's within that 90%. Am I making sense? Do this whole thing a number of times. Of course, you're going to need your calculators, ladies and gentlemen. Start bringing them. You're going to pull out your phones, your calculators, get ready to do some math. So you have to do this. You have to add them up. What are you going to add up? The difference between these two, right? The difference between how many different ones do we have, by the way?
4.
So what is our degrees of freedom? Degrees of freedom. What are they? Somebody remember how we calculate degrees of freedom? 4 minus 1. So how many we have? Minus 1. So 4 minus 1 is 3. So we have 3 degrees of freedom. That's going to be important in just a minute. So we're going to have to do this probably 4 times in this case. So one for each of our values, right? We're going to compare. What are we doing? Comparing our expected to our observed. Comparing our expected to our observed. Please stop closing your eyes. Go wash your face. Stand up. Whatever you got to do. I understand you're tired. I get it. If you're sick, go to the office. Sign yourself in the office, and you got a little space over there. You can lay your head down. But sleeping in class, it's rude to me. It's rude to everybody in the room. So you have to sum these up. So how do we do that? We're going to take the observed, the first one, which is 400, And we're gonna add, or subtract what? Oh no, I messed it up. 404. And subtracting 400. And then I'm gonna square that, and I'm gonna divide it by 400. Then I'm gonna add that to, this is what the sum means. This is what the sum means. I'm gonna add it to, again, 420 minus what? 400. Now that's a negative number. Oh no, I messed it up again. No, it's not negative. How is it negative? I'm confused. Of course, we square it, and then we divide by what? By 400 again. We're going to be dividing by 400 in this case all the way across, right? Then we're going to do what? 400 minus 400. Squared, of course that'll be 0 squared, which is 0, divided by 400, which is what? 0, so we're still good. Man, this is getting a lot. Now we get, I was jumping ahead in my mind, that's the problem. And he's got 376 minus 400, and we're squaring it. Wait, it's negative. Is it? The answer's not going to be negative. Why?
Because you're squaring it.
Because it's square. Remember the square. So divide that by 400 again. Add those all together. Who's been doing the math?
It gives you what's 3 points?
Guys, somebody do the math. Let me pause it here. You got 2.48. I'm going to go with that. Somebody can find something different. Let me know. 2.48. That's your chi-square value. There it is, 2.48. Whee! Yay! What does that tell us? We really can't tell anything. It doesn't tell us anything, does it? So we just added them all up. We took all those together. Somebody did it. Few people got 2.48, so we'll go ahead and accept that as the value. And what happens is that we came up to a problem, and what's our problem? Our problem is we don't know what that number means, do we? What does it mean when we have a chi-square value of 2.48? Does that mean it's important, or does that mean it's not important? What's the next step? What do we have to do in order to figure that out? No, divide. No, there's nothing more to the formula.
Then you gotta look at the graph or
Not graph.
the belting.
Not the belting. It's not a graph. It's not a graph.
The bell curve.
It's not a. It's a table, right? Do you remember the table?
No.
You don't remember the table. This is what the table looks like. Let me switch the screens for you.
Oh, I think I know.
I showed it to you yesterday. It looks here. This is what the table looks like. You had it up on a screen. The YouTube video we watched in class on Friday had that table. Required you to figure out it required you to. I sent it to you. Told you to make sure you finish it for the weekend. No, okay. So degrees of freedom is on the right. Do you see that R? See, it says 1, 2, 3, 4, 5.
No.
Oh, I didn't switch it. Oh, you're so rude.
I'm not rude.
That R, it says 1, 2, 3, 4, 5. See it?
Yeah.
That's your degrees of freedom. So our degrees of freedom was what?
3.
It was 3, right? 4 possibilities minus 1 is 3. So if you look at it, let me zoom in a little bit because I'm sure some people are going to start complaining they can't see. So here's 2 degrees of freedom. Remember, what number are we going to use? Point what? 0.05. So at 0.05, with 3 degrees of freedom, anything less than any difference, any chi-square value that's 0.352, right? 0.352. that is a table, right? Any chi-square value that is greater than 0.352 means that it's significant, and we reject the null hypothesis.
So that means that's
Ours
a
is less, so.
no, there's some
No,
more.
it was
There's
more.
3
Way
more
ahead.
and 1. No, they're all 1.
Our value for chi-square was 2.48, okay? When we go back to the table, if that value that we find off the table at 0.05 with 3 degrees of freedom, if our value is greater than 0.352, which is what we're getting off the table, right? What do? We reject the null hypothesis, which means something else is going on. Our value is 2.48. It's greater than the value given to us by the table. So we reject the null hypothesis and we say something else is going on here. There's something weird. Somebody has cards in here, too many of this card or too few of those cards. Looking at the value of the cards, you wouldn't even guess that, really. I mean, you might guess it, but you're looking at these values. I don't see a big difference between these. I would have guessed that they were pretty close to what the expected value is. But the calculations tell us that there's something else going on. And that is chi-square. You're going to get some practice problems assigned to you tomorrow. We're running out of time today. Tomorrow, anyways, so questions 1 and 2 we already went over, and I think people understand it for the most part. It's, dealing with playing cards. Most of you work with playing cards.
I don't think we went over to it.
I don't, but I've uploaded this document to your Jupyter grades, and you should be able to access them. And if you need to, you can print them in the building, and even if you're leaving, I think before you go to advisor, I think
The hallway printers don't work.
hallway printers, I think even so, you can print them in your advisory teacher has a printer. Can we just try to, okay, I'll just sit here and be quiet, because I'm not gonna sit there and just keep having you comment back and forth while I'm trying to give you information. So whatever the issue is, if you don't have, I handed you a copy, if you lost it, print it. Okay, that's all. All right, number 3, I'm going to read the problem, and I'd like to go over how do you get the expected. I'm not going to do the whole problem with you, but I'm going to help you with how do you do the expected, okay? So genetics engineer was attempting to cross a tiger with a cheetah. Now, when I see a problem like this, any kind of word problem, I'm telling you right now, what you need to do is you need to kind of draw it out. And don't worry about taking notes. I'm sending this to you before the end of the day, right? And you should be able to take notes when you get home. But if you have pencil and paper, take notes. Genetics engineer was attempting to cross a tiger with a cheetah. And so you're saying tiger. And see, notice I'm not writing out the whole thing. X and a cheetah. All right, so I know a cheetah and a tiger are going to be crossed together. And she predicted the phenotype outcome of the traits. She was observing the following ratios, right? 4 stripes only had stripes. 3 had spots only. Both 9 of them had stripes and spots. All right. When the cross was performed and she counted the individuals, she found that 50 had. Oh wait, so this is what she expected. So they gave you what was expected already. And then when she did the cross, she found 50 with stripes only, right? And 41 with spots and 85 with both, right? stripes, and spots. Does that make sense to you?
Yes.
All right. So this is what, the bottom is what she observed, and the top is what she expected. Now there's a trick to this problem, and they're asking you to do the chi-square. Now the trick is subtle, but it's there. So this is what she would have expected if she had this many. What was the total here? What's the total?
16.
So we have 16 total. And what's the total here? One what? Somebody 176. The problem with this is that there's no real hypothesis, right? The only hypothesis is that you expect to see this. There's no, in a real genetics problem, your hypothesis would be codominant. Does that make sense?
Yeah.
And you have to, and because they don't tell you that, it's just a math problem, so it's not really a genetics issue. All right, well, whatever. We have 4 stripes, so what's the total? We say it's 16. So we expect 4 out of 16. What's 4 out of 16? What's the math of that? 1/4. So you expect 1/4. You'd expect to see 1/4 in that's what she expects, 1/4 of these to be stripes. And what's 3 out of 16?
4.
3 out of 16.
Oh, shoot.
Which, by the way, is equal to 0.25, right?
What's 3 out of 15? Like you saying with a fraction form?
Yeah, 3 out of 16 is what decimal?
Shoot. I'm about to give that to you. Don't answer them. Don't answer them. I got it. Hold on.
Yeah.
Hold on. Don't say it. 0.1875.
All right, so this is 0.1875. And what's 9 out of 16?
I got it. Eat that. I'll trim off.
Yeah,
0.025.
0.025. All right.
Sir.
So that's what we expect. So what are going to be? So how would, when you're doing chi-square, what different answer did you get? Where?
0.5625.
For what?
9 out of 16.
I think that's more reasonable.
You think that her answer's more reasonable?
Yeah.
What did I just give you? 5? I meant to say 5625. My fault. That was serious.
What was it now?
5.
5625.
Yeah. Serious.
0.5625? That's more reasonable.
Yeah, that's the answer.
Because 9 out of 16 is a bigger number than that was. All right, so anyways, let's do the math. How many stripes would you expect, given that these were the actual number of babies, right? 176 were the actual number of babies. What would be the expected now that you know how many babies were born, right?
Yeah.
So-
How did she get 4?
I don't know. That's my problem with the problem. I don't know why. Well, I don't know where she got these numbers. It doesn't matter. Let's just do the problem. We're just doing the problem, right? Because it doesn't make sense. Like biologically, it doesn't make sense. So let's just do the problem. 176. What's 0.25 times 176? What? 44.
What you said?
We're taking 0.25 and we're multiplying it times what?
176.
176. Why? Because that's how many stripes she expects.
Right. Now,
So that's 44. So these are my expected. 44 what? 44 stripes. And the next one, how many spots? 41 out of 176 is what? 33. And what are you doing there? You're taking 0.1875 and multiplying it times 176, right? Okay. And last one's 0.5625. And what is it? 99. So what you really expect, the actual expectation is 33 spots, 99 stripes and spots.
So are we changing the number?
No,
All right, so let me-
we're expecting.
So this is what she stated she'd expect if she had 16 progeny. But you didn't have 16 progeny, did you? What did you have? 176. So the first thing you had to do is figure out what was the ratio or percentage or decimal form. What was the decimal of your total? And so since 176 was the actual number of the babies that were born, and she got this number of stripes, this number of spots, and this number of stripes and spots, that's what you observed, then you had to translate this expected into a number that's related to the actual number of babies you had. Does that make sense? And so the actual expected now is this. So you observed this and you expected that. I'm not going to do any more with chi-square. You know that the chi-square formula is the sum of, right, a number of units, and those units are the observed minus expected squared divided by the expected. You can put the little I here if you'd like. So you'd have to go ahead and do this for stripes, and then you do it for spots, and then you do it for stripes and spots, right? Then you add all those together, and that'll be your chi-square. What are your degrees of freedom? Anybody?
The
2.
2 is your degrees of freedom. How did she get 2? 3 possibilities. You have stripes, spots, or stripes and spots. So there's 3 possibilities. Minus 1 is 2. So that's your degrees of freedom. And then you go to your chart and you compare your chi-square. That's the sum of all 3 of those. You compare that to your row with 2 degrees of freedom at what critical value? What's your critical value? That's right. Is equal, the one we use, the one we think is significant, that's usually accepted as significant, is 0.05, right? So you go to that column. How do you get that? I told you this. I'm telling you that. In different problems, they might tell you to use a different critical value. But in general, the critical value that's expected is 0.05. That's kind of the standard. Yeah, there is a chart in the packet. It's the last page. Again, you have the electronic version there as well. Also, it has the steps of how to do this there as well. So please read the steps. It's there for you. I want to remind you that in the steps, number 5 was not separated from number 4. It says 4 point, and then there's find the different the degrees of freedom n minus 1, and then it says 5, find the table values. So they're kind of on the same row. All right, so let's quickly the next one. At least set up the next one. Hopefully these guys follow a little more genetics than the previous problem. In the garden pea, yellow color is dominant to green color, right? So now they're telling you yellow is dominant and green is recessive. I like to put the little tail on it because that way I know when I'm doing it, I know which one's yellow and which one's green, which is dominant, which is recessive. The inflated pod is dominant. So this is inflated. And the constricted pod is recessive. Notice I put the little curly Q on the I and a little dot. I'm just letting you know that it helps when you're doing these problems to make sure you have some way of making sure you can tell the difference between the uppercase and lowercase. So, by the way, remind me to tell you where uppercase and lowercase comes from. I just found out I was watching a British show the other day and I found out where that comes from. It's really interesting. Consider both these traits and jointly in a self-fertilized dihybrid. So now we know we're talking about dihybrid now, right? So that's what? That's big Y, little I, big Y, little y, right? Big I, little I, crossed with what? Big Y, big I, little I, right? Dihybrid cross. And what are going to be my gametes? Now, quickly, before I even start to look at what is this helping me with? This is helping me with the expected. Where am I going to, this is what I observed. They observe 193 green, 184 yellow constricted, 156 yellow inflated, 61 green and constricted, right? How do I know what I expected? I need to do the Punnett square. But do I really need to do the Punnett square? What do I really need to do? What should I have memorized with a dihybrid cross? I heard it. 9 to 3 to 3 to 1. So the 9 is a double dominant, right? So the 9 is big Y with big I, big I. Oh, no, I'm sorry. That's not true. The 9 I expect these are phenotypic ratios, right? So big Y blank and big I blank. 9 of them are going to be like this. Does that make sense to everybody? Is this confusing to anybody? Please say so now. It's okay if it is, just say so. So the reason since I don't hear anyone, but I don't see anyone saying, oh wow, I got that, I'm going to go ahead and say this. 9, if you do the Punnett square, I'm not going to do it here because we're running out of time. If you do the dihybrid Punnett square, right, what you're going to find, you're going to count 9 are going to be a big Y and a big I. It'll be big Y, or big Y, little y, or big I, or big I, little I, but whatever, you're going to see a big Y and a big I 9 times. Okay? Okay, 3 of those in those 16 squares are going to be a big Y, and it's going to be a big Y blank with little I, little I. So you're going to have one of the traits are going to be recessive, and the other trait's going to be dominant phenotype, is going to show up 3 times out of 16. Is that clear? Okay. And then the other 3 is when they have little y with big I blank. Again, you're going to see the inflated phenotype 3 times, whether they're yellow or green. Does that make sense? And then, of course, only one of those 16 is going to be little y, little I, which is green and constricted. So you're going to have 9 that are going to be yellow and inflated. You're going to have 3 of them are going to be yellow and constricted. And you're going to have 3 of them that are going to be green and constricted. Do you see that? Oh, I'm sorry, my bad. Inflated. And you're going to have 3, only one of them is going to be green and constricted. Does that make sense? How did I know that? I've done the Punnett square. I memorized my 9:3 to 3:1 ratio. I know that those are phenotypic ratios. I've memorized this. I can use this to my advantage. I don't have to, in a multiple choice test that the state gives me, I don't have to figure that out. I know that. So, okay, so here's this dihybrid cross, yellow, green, constricted, etc. So now the next question is, how many of if I tell you that the observed, this is all stuff that I knew before I walked in. Before I walked into the problem, they didn't give you any of this in the problem, right? The only thing they told you is what was dominant, what was recessive, right? Okay, the other thing they gave you is 193 green inflated. Then they gave you 184 was yellow constricted, and the 556 was yellow and inflated, and then 61 was green and constricted. Is everybody okay with that? All right. So that's what they give you. This is the observed. These are the observed. Now you have to find out the constricted, the expected. And you're right, we're going to have to add it up because we need to know the total. How many babies were actually born, just like in the previous problem? How many progeny did they actually have? Can someone add these up quickly? What is it? Should be 1,000 something. No, maybe not. So, yeah, anybody just, I'll wait for a second. I think we have time.
994.
So it's 994 of them. So the total is 994. Right? We're good with that? So how many did you expect of each of these? Well, I'd have to take my percentage that I expected, which is up here, right? 9 out of 16, to find what? What would be 9 out of 16? What percent is 9 out of 16? Yeah? 0.5625. So what would that be? What do I expect to be 0.5625 of the total? Green inflated. No, not green inflated. Yellow inflated. See, yellow inflated. This guy. This is the 9 out of 16. So the yellow inflated, I expect to be 9 out of 16, or 0.56 what? 24? 25. 0.5625 times 994. Somebody do the math. Type it into the calculator and let's see what we get. What number would you expect?
559.
559, and we're gonna round it up and leave it alone, 559. That's what we expect. Now, what about yellow constricted? How many would we expect? Yellow constricted. That's 3 out of 16, right? Look up at the top. Yellow constricted's here. I know it's hard to see. What is it?
0.1875.
So 0.1875 times what? The total again, 994. Don't multiply times the observed, multiply times the total. 186. So 186, and we're rounding. And what is, how about the green inflated? How many, that's, again, 3 out of 16, so we don't have to do the math on that, we already did it, is 186, right? What about the green constricted? 1 out of 16, which is what percentage? 0.0625 times 994 is what? 62, so we expect 62. Look how close they are. Now some of you might say, well, it matches, right? But we don't know we don't know how far away. It looks like they're very close, doesn't it? This is 62, this is 61, this is 556, this is 559. But to really figure out if it's actually significant or not significant, the difference between this series of numbers, the observed and the expected, we have to do what? Chi-square. So now we just do the chi-square, and that's again just simply the chi-square, which is that weird looking x, which is a Greek letter, is equal to the sum of, right, the observed minus expected squared divided by the expected. What is the degrees of freedom here? 3, excellent. The degrees of freedom is 3, and how did I get 3? There's 4 possibilities, and I said minus 1. You know what? I've often asked that, and I've looked at and I really don't know the answer to that. All right, I've heard the answer. I've heard an answer that was interesting. I'm not sure how valid it was. I've looked on YouTube videos. I'm not familiar enough with statistics to tell you what exactly it means and why we do it. All right, I've actually taken classes where they've explained chi-square and they've just said just do it. So I'm just going to tell you that that's part of the process. It's not magic. I'm sure there's a really good reason for it. I know there is. What it is, I'm sorry to say your teacher is not that well informed on the details of that. Yeah.
You do chi-square for each possibility, right? Like the observed minus the expected.
That's right. Good. So here's the trick. I'm going to disagree with you a little bit on what you just said, but I know that fundamentally you're right. Okay? The part I'm going to disagree with you is that see this symbol? The sum? That means you're adding stuff up. What are you adding up? What are you adding up? You're adding up this part of the equation, right? This observed minus expected squared divided by expected. And what you're doing that 4 times, aren't you? You're going to do that here with this number, you're going to do it with this number, you're going to do it with this number, you're going to do it with each of these possibilities, right? And then what are you going to do with all those? You're going to add them. That's what this symbol means. So chi-square, this is your chi-square. This is chi-square. Does that make sense? So even on your paper, even in the handout that you had gotten initially, it said the sum of the chi-squares. That's not true. Chi-square is the sum of observed minus expected squared divided by expected. Is that clear? That is what when someone says chi-square, that is this one added to this one, added to this one, added to that one. Okay? That is what chi-square means. All right, and once you get that chi-square, then you compare it to your third row at 0.05 with a critical value of 0.05 because that's the one we use. And the table's there. And then you decide what? Do you accept the null hypothesis or not? And what is the null hypothesis? It's going to be a really big deal for you in AP biology, certainly in statistics. the difference between the question that you're trying to answer, do you all agree that there is a difference between the expected and the observed?
Yeah.
That's science, guys. We rarely ever get exactly the number we expect. We often get numbers that are close, right? I've told you that throughout your genetics chapter, right? I said, listen, you expect 1/4 of these guys to be albinos, but you could have 10 kids and none of them could be albinos, right? Or all of them could be albinos, right? So there's always that variance, that randomness to it. And so is this due to randomness or is this due to something actually being else going on? Is the theory wrong? Is there some other influence happening? We don't know until we do this chi-square comparison. How well does this fit, and do we expect, and remember what this means. This means that curve where this is the number we expect, or the average, right? And we have these areas way on each side of these, right? That we say, this is significant. This is significantly different. If it's if it's anywhere in here, then we're okay with it. If the number falls over here, we're like, there's something else going on. It's significant. And that's what you're looking for. You're looking to see if chi-square, and I'm going to say it really clearly, if chi-square, notice I'm doing that chi-square thing, is greater than or equal to your critical value, then you reject the null hypothesis. You reject that the difference is due to random error. You have to accept the alternative hypothesis, which is something else is going on. What that something else is, that's the science part, right? This is the math part. This is also science, but it's our language, right? So when we sit there and we're trying to compare, is the number relevant or not? Well, you've got to make that comparison. By the way, do you see how you're going to use this in math? How you're going to use it in history, in social studies? Here's a question. Was there an influence of Russian meddling in our electoral system in the 2016 presidential election?
Yes.
How are you going to make that decision? You're going to have a bunch of numbers, and I don't know the math. I'm not a statistician, right? But you're going to have some expected values. You're going to have some observed values. You're going to compare the two somehow, and you're going to make some kind of mathematical statistical analysis that's going to compare the two. You're not going to say yes or no like so many politicians do, right? You're going to make a scientific study of it and really compare the two and really say, okay, objectively, it looks like something is going on. Or objectively, the difference is due to random luck. Right? And that goes to anything. You do this in anything, everywhere, all the time, in business, in history. One of the major ways people make money, one of the most important jobs out there, is statistics. As a doctor, you're constantly looking at epidemiological studies. You're looking. How does someone know that smoking causes cancer? How do you know that smoking causes cancer? Statistics tells us this. It's looking at how many people do we expect to have cancer? How many people, and we have some way of analyzing that. We come up with some expected value. We look at how many people actually have cancer. We compare those that smoke versus those that don't smoke. And we see, is there a difference? And if there is a difference, is it a significant difference? Or is it due to random luck? Every question is answered like this in some way. Chi-square is not the only way to do this. There's several other ways to do it, many other ways of doing it. In fact, you can get a whole degree, a PhD in statistics.
Our expected value off by one.
Your expected value what?
Total is off by one.
I don't know what you mean by off by one.
The total of our observed and expected is off by one.
What do you mean?
It's one less. Our total expected is one.
Are you talking about the critical value versus your chi-square?
No, I'm talking about our observed total, like the 994.
Is 993?
Yeah.
Oh, I see. Yeah, it's going to be off by one because we rounded off. There's rounding error in this. So, maybe we should have went ahead and just kept the decimals. But that, to me, that never makes sense, right? Like, why would you have 61.25 plants? How is that possible? But maybe mathematically, we should have kept the decimals and then would have worked out better. It reduces your error, right? And we call it, there's actually a name for it, it's called rounding error. We expect that there's gonna be some rounding error. It's an error that comes when you start to round, and that doesn't make you as accurate. But of course, there's also these other things that we call significant digits that we try to control that with. And you'll learn more about that in physics and chemistry. Are we good? So this is how you do these problems. And really it's kind of easy once you get to know the vocabulary. Make sure you know what chi-square is, make sure you know what how do you find the degrees of freedom, how do you read the chart, remembering that critical value is always 0.05, then life is really easy. And especially if you know your ratios, 9 to 3 to 3 to 1. By the way, those of you retaking the genetics exam, you're going to have to know those ratios really well, because there's like 4 problems about those ratios. So make sure you do that.
Is that how you spell critical? You wrote it with
Is it? I don't know. I might have wrote it, misspelled it. You know, I have, especially when I'm talking to you and I'm writing at the same time, I often make mistakes in spelling. You guys have to help me out and catch me on that, otherwise I'll embarrass myself.
Do we move our decimal point when we try to figure it out?
I would just leave it all up and then just compare it. In fact, I'll tell you, if you really feel more comfortable not rounding, you could try not rounding, and you'd probably get closer to that, and the totals would be much closer. But bottom line is the number bigger or not? Usually it's not. When a number is bigger than the critical value, when a chi-square is bigger than the critical value, usually it's not a subtle difference, right? It can be equal to, it's possible, but, and there's always that room for like, if it's like 0.2 off, if the two are like, if it's 0.2 bigger than the critical value, is it that big a difference? Well, this is all what? What are we doing? Best guess, aren't we? Isn't this all about best guess? Because do we really know what's going on? We don't see it happening.
No.
We weren't there. We're just making our best guess, and we're using the most objective ways of measuring it. That's what science is. Okay? It really is about best guess. A doctor tells you he thinks you have X, Y, or Z. Does he know?
No.
He'll tell you, all the tests indicate that you have this. We think that this is the best course of treatment. Why do they say that way? Because most people that have your symptoms have this problem, and this helps most people that have that problem. But could you have something else?
Yes.
Sure, it's possible. But the doctor's making his best guess based on statistics, based on facts, based on past experience, right? And it's really a good guess, because a lot of times they help, don't they? They help more than they hurt. So you have to make sure that you understand that that's what science is. Don't go out of a science class thinking that so-and-so knows everything, so-and-so knows everything. We don't know everything. Life is not about knowing. This world, the human condition, is about making our best guess based on the science, the information we have. And moving forward, that's what you're training to be. A person is really good at looking at the facts and making decisions based on the facts. And could you be wrong? Yes.
So wait, I can find the probability of me marrying my cousin.
There's all kinds of things you can start finding. That's what science is. That's it. All right. So it's 9:43. We're supposed to leave at 9:57. I'm going to suggest that we go over some of the stuff that's in the rest of this video, okay, that we already went over yesterday. Is that okay? All right. So I just want to remind you, you got those 4 assignments in the ebook on chapter 17. By the way, some people are there's some people are having trouble seeing them because in the drop arrow boxes, there's a bunch of old assignments. I have to double check the due date. Maybe the due date is mixed up, but all the assignments are there. If you keep hitting the down box, the down arrow, you will see the assignments. They're all there. I have the old assignments still there because some people said that they wanted to access those, so I moved the due dates for the old assignments up, right, so that you can see them. So you'll see chapters 9 and 10 in there already as well. Please don't worry, unless you haven't submitted them already, don't worry about those assignments, obviously. Somebody said there's 13 assignments. Those are old assignments. Those are old assignments. For this weekend, you have 4 assignments in the ebook. 4. Of course, last weekend you had how many assignments?
Like 2.
3.
Oh, 3.
You had 3. So if you didn't do last weekend's work, you got 7 to do this weekend. I mean, it's not horrible. It's not really isn't bad. And you have this weekend's chapter is important because we're going to start talking in a second on chapter 17. This is what chapter 17 is about. This is why we do chi-square in biology. What we just saw in genetics, and what we're about to do with alleles. We're going to talk about population genetics.
Oh.
So now we're going to look and see what frequency of alleles are there in a population, and how do we figure out what are the chances of this happening? Is evolution happening? What is evolution? Is it happening?
Yeah.
So that's what we're going to try to answer in chapter 17. So you really need to know that. I'm telling you, you're going to be tested heavily on it in your end of course exams. And they're coming up soon. In class, we may or may not meet because tomorrow's Thursday. We're having Black History Month. If we don't meet, we will go over the evolution of populations, which is next. The reason chi-square is important is in any science, or something like that, a goodness of fit, is because in any science class, any science work, you have to question whether your answers match your theory. And that up to now, I think in your educational career, it was obvious, right? Either it was a yes or no answer. It was pretty obvious when something wasn't following theory or was following theory. Something fit, the data fit your expectations or didn't fit your expectations. It was clear to you. Either it was not on the line, or it was, it should have been blue and it turned out red, then you know it's not. Kind of real simple yes, no, dichotomous choices, right? One way or the other. That's not how the real world is. The real world, you get data, and the data comes close, but sometimes, most of the time, doesn't match exactly what you're looking for. And the question always comes up, how good is this data? Does the difference between what I expected and what I observed, is that difference significant enough for me to change the theory or not? There's constantly a question in your mind in science. Well, one of the theories that we have that explains our observations is evolution. Evolution is a really big idea. And populations evolve. Let's be clear on this. A lot of people, the problem that we're having in our society, one of the many problems, I guess, but one of the problems is that we have these ideas about evolution. And we just keep, X-Men, and we're evolving towards some kind of great final step in our evolution as human beings. We're going to finally evolve to become some kind of ascended being or something like that. That's not how evolution works. So that we have to try to forget about what we think evolution is and just keep it simple and look at what evolution really is in a scientific realm, in the scientific point of view. So when we're talking about evolution, individuals, you as a person do not evolve when we're talking about biological evolution. We as a population evolve. Populations evolve. Write that down. I promise you that's going to be a test question on your evolution exam. So populations evolve, not individuals. Mutations happen in individuals. Evolution happens at the population level. Okay? And let's take a look at this cartoon. I always like little comics because comics help you understand. Populations evolve, mutations happen to the individuals, and populations evolve. The scale issue that people keep having. So let's take a look. And one of the problems, I got to warn you right now, when you go into a history class, you go to a sociology class, or you're in college and you're taking a sociology class, they're going to talk, you might even read a book, The Evolution of Women, The Evolution of Jane, Jane's evolution into a new person. They're using evolution in that context, not as the biological evolution that we're defining in this class. Is that clear? So there's a scientific, biological definition of evolution, and then there's evolution used in common day language. They're two different ideas. Even though they're very related, right? They're not directly related. They're not one for one. So don't get confused. So here, let's take a look at this comic book. Here's this little bird. Everybody else flew away. He's left. Of course, what's going to happen to him? He's about to get eaten, right? And they call it natural selection at work. This is natural selection, right? So this bird had some genes that, for whatever reason, he didn't fly away when everyone else flew away. And what happens? He dies. Does he get to send his genes to the next generation? Does he have babies if he's dead? No, no babies. So no gene. His genes don't go on. Those that had the genes to react like everyone else, they're gone. The only ones that are left are the ones that didn't have those genes. So he's dead. And that explains why every time you see a bunch of birds and anything happens, they all take off. Do you ever see one bird just kind of hanging around afterwards like, No, that never happens because those birds are what? They're dead. I'm sure it happens once in a while, but they quickly die. So he says, do those sweet-sounding bells seem to be getting closer, or is it just me? So he didn't get the gene that allows him to react to everybody else leaving, right? He doesn't have that social gene that allows him to react as a group. All right, so something about it. The key to evolution is not, there's several points, and we'll make it in a minute, but there's let's write it down now so when we're going forward, we have these kind of things in our minds. Number one, you need genetic variation. These are keys to evolution, right? These are kind of foundations. Genetic variation. You have to have a bunch of genes to choose from. We got to remember that we get genetic variation from what? Mutations, and we get it from meiosis, right? Specifically crossing over. So that's our genetic variation. And of course, that's key to evolution. You have to have differences between individuals. By the way, it's kind of an asterisk, it's kind of an aside. I'm going to go ahead and put in kind of square brackets. Remember that is the advantage of sexually reproducing organisms. Does that make sense? Remember that from our discussion earlier in the previous unit? The fact that we are sexually reproducing organisms, our species has sex to have babies, that's an advantage over a tree that only sends, or grass that just sends its roots out and it's just a clone of itself, right? The problem with that is that they don't have any genetic variation. So if something happens, a natural disaster happens, then the entire group dies, the whole population dies. Where we as a sexually dividing, reproducing species, we have genetic variation. Look at us, we're varied. Even in a group of all blank, fill in the blank, right? No matter where you are, in the same family, you could be in the same family, you could look around and see, you know my brother, you've seen him. We're genetically varied, right? We look very different, even though he's my brother. And so when we're looking at any kind, because we're sexually dividing creatures, there's genetic variation in every population. That's an advantage, that's a good thing. Because if something happens in my family, we're all very different, and if something happens that kills off a bunch of us, it'd be lucky that one or two of us will survive and we'll keep being able to have babies and move on. Where if we didn't have this genetic variation, it would seriously limit our capabilities to deal with natural disasters, with things that kill, right? That's what we're talking about. The second, this is a driving force of evolution. So one is you have choices. The next thing is the thing that makes the choice. What is the thing that makes a choice? We call it natural selection. What does that mean? Anyone?
It's like,
You want to answer? Go ahead.
Isn't that just when it's like you can't like figure it out, it's just whatever happens, it's random?
No.
That's not right,
It's by definition, it's not random. Natural selection is not random. The randomness comes in the genetic variation. But this is not random. Natural selection is not random. It's actually the opposite of random. There's a choice. Selection, you're choosing. Yeah.
Isn't it when it's certain genes don't work out with certain environments, and so they're weeded out through death?
That's right. That's it. So certain genes, and therefore the products they make, right, proteins, give you traits, right? We've been going over that. Remember the pedigrees, the Punnett squares. You have certain genes give you certain traits. Those traits make you different. You're either dark or you're short, you're tall, you're fat, you're slow, you're fast, you're smart, you're not, whatever, right? Whatever the traits are, you are different from everyone else in the room. Those differences allow for when the environment changes, somebody dies and somebody lives. That's a big deal because the person that died can't have babies and therefore their genes will not be in the next generation. And over time, that changes the population. So natural selection is death. Selective selection of environmental I'm sorry, that is wrong. Selection of survivors by the environment. All right, so selection of who survives, who doesn't. You've heard of this idea, best what? Does anybody know? Best fit to survive. It's best fit. Who's the fittest?
They say that a lot of movies.
They say in a lot of movies. This is something that's said in a lot of books. It comes from Darwin's original concepts. Best fit to survive. You have a population, there is a group of people in here, one or two, or maybe it's just one, maybe it's a group of us, are better fit to survive than the rest. And something happens, the rest die, the ones that are best fit survive. Understand something. My problem with best fit is that people think of fit as someone who's in shape. For one, I will be publishing videos and stuff, publishing this afternoon. I have to tutor this evening, okay? So I won't be able to do it right away, but as soon as I get home, get settled in at home, I'll get the videos published for you. Number two, the due dates on everything. If you get everything uploaded, I would assume by the end of today. I probably won't get around to checking it. The work that's due today till this evening. So if you want to upload it before before I get to check it, that's good. If I check it, it'll turn into it's not there. It'll be a 0. But then just turn in, right? And then tell me that I need to check it. Just give me 1 second, and then I'll get to questions. So you have till the end of the today, probably around 6, 7 o'clock, to get that uploaded. So that's the chapter work, is what I'm talking about. And I believe it was 17, wasn't it? Chapter 17.
I thought it was 15.
It was 17. I think is.
It was 15 because it was evolution.
Oh, it was evolution. All right, yeah. It was one of the two chapters. It was 15 and 17. I can't remember which one it is. So chapter 15 work, it should be, the evolution stuff should be done by now. So when we go on and talk about it in a minute, you're going to be able to quickly get through it because we already talked about it, right? Mm-hmm. So chapter, you already read it rather in the chapter. And there's 4 assignments here. I only have a place for 3. The 4th one I'll make due tomorrow because I didn't make this. It's not right for me to expect you to turn in today since I didn't put it in, right? So that 4th one, you'll see that by name. They're named as per this assignment.
Mister.
Yeah.
I messed up and put them all in one.
Well, you have time to correct it. So you don't have to do it right away. You have probably till 6 p.m. tonight. So maybe a little later. So the next thing is this chi-square work. So the chi-square work, that's going to be related to the video I got to publish for you. So I didn't tell second block, but I'll tell you, I'll move the date back to Wednesday, all right, to give you time to watch the video. The video is going to give you a little help, okay? If you did it and you uploaded it, great. If you did it and you're ready to go, then, just upload it when you can. You can upload it anytime you want. All right, so that takes care of that, the work. And let's talk about ProCore, NWAs, all that stuff real quick, and then we'll move on and talk about what we have to talk about. Yeah?
Before we do that, so the chapter work is, you said we didn't have to, so ways that we can do it, you want us to upload it, but we don't have to print it out, we can like take a picture of the screen.
You can take a picture of the screen, you can print it out, you can handwrite the answers, you can take a picture of it, you can send me a PDF. I'll accept whatever you got,
Okay.
right? You can make a Juno doc and write the answers right in the Juno doc and then put that in there. You can make a Google doc and send me and put the link in there. There's like 10 different ways of doing it, however you're comfortable. I'm cool with all of it. Just get it submitted, that's all. And those of you that turn late work in, great, I'm glad. I know it's a little frustrating because you're working hard. I had a couple kids this morning in class during advisory. It was like, broke my heart. But I know some kids are working hard. And one kid told me, well, I'm going to fail anyways. I'm going to fail the test anyway, so why should I come and retake it? It doesn't make sense to me that people have that attitude. You should not have that attitude. I try to teach this to you over and over again. When you fail a test, it's not a judgment on you. This little girl felt that she was no way she was going to pass this test. And I said, look, most people pass this test. There's nothing, no one in this school is better than you. You're no better than anyone else, but no one's better than you. No one's smarter than you. Most people, there might be some geniuses around. I don't know who they are, if they do exist. Unless they're a genius, you're pretty much all the same intelligence. You understand that, right? Some of you have different experiences that give you advantages than other people. I get that. But that doesn't make you somehow superior to someone else. Everybody in here can do it. Some people have experiences that are not as in-depth and rich as others. And so it takes some people more work to get the ideas through. That's okay. But that means that you have to do it. I'm here to help you. I'm going to be here after school if you need tutoring. So no one should be judging themselves and I'm saying this to the crowd because, as I said, this little girl had a really adverse reaction when I called her up and I said, listen, you got to come and see me after school and let's go over this stuff. I will walk you through the test and then I'll give you a test, it'll give you a retest and you should be able to do it. Even if you don't ace it, you'll do better, right? The goal is not perfect. The goal is perfection, but really, if you don't get it perfect, you get 90%, it's still an A, right? Okay, you guys gotta kind of stop taking things so. No, I want you not seriously. I know what you mean. You need to stop taking it so personally. All right, it's not a judgment on you. It's a grade. It says, gee, Jimmy, you didn't get this. Come and figure out what you didn't get and then try again. That's all. I didn't pick Jimmy because it's my favorite name. I wish I was Jimmy. All right, so anyways, I grew up in a Polish. It was Polish at the time, then turned Italian, and then Irish. And
The word you.
no, the neighborhood. So I grew up with a bunch of skis, right? And then I grew up with a bunch of Antonies, right? Everybody was Antony this or Antony that, Maria or something like that. And then that's Italian names, right? There was a lot of Italian names. And then it's a long story. Who cares? You don't care. I don't care. Anyways, let's go on. So we're good with this? Now, NWAs. Look, next week you got NWAs. By the way, did anybody in here do their CFLs today? Some people did, some people didn't, right? So you're going to probably have to do CFLs. You know that throughout the week, this week, we're gonna do your Friday meetings, or Friday, not Friday meeting, what am I saying? Your white coat, right? We got white coat going on. It's kind of crazy week. You got white coat happening. You have CFLs to complete if you haven't completed. You have your NWAs, both the English and the math, right? I think most of you, I think, have both, right? Yeah, I think everybody here has both. NWA, the upperclassman, I think doesn't have it, but I don't know. But anyways, you have to finish English and math and the NWAs. You know that you have to show growth on those and that kind of stuff. But the key is that takes out 2 days. It's gonna be kind of crazy next week. You still have, in 2 weeks from now, you have your ProCore. So you have your ProCore biology. You have your ProCore biology exam. It's it. It's time. Ouch. Now the ProCore, well, in a second, if you don't mind. A ProCore biology, unless it's an emergency, then yeah. In ProCore biology, the couple things we haven't finished is evolution, and then we're going to talk about ecology, and then we have to review. There's not going to be a lot of time for review. We're really under the gun here. So this is what I've been worried about for a long time, and I want you guys to show growth, because this is going to be, for my class, a big part of your final grade. You know how you have a final at the end of the year? For me, for my class, right, every class is going to be different. All you're going to do is a project during finals week. Because guess what? For my class, you will have already done this test, and we will have already the scores back from ProCore by finals week. So I will know how much you've grown. If you show growth, that's going to show that growth. How much growth you've shown will be will determine your grade on a part of your grade on your final.
What if you don't grow no way?
Right, then you don't do well on that part of the grade. Does that make sense? So now there are some questions for some people. Like, what if I did well in the fall, but then I don't do because I did so well, I don't show that much growth in the spring test. Well, I take that into consideration as part of the formula. So if you scored, I'm just gonna make up some numbers, all right? I don't even think these are real numbers, but I don't know how they just give me a report and they tell me how much you've grown. Right, but let's say you scored 80% on in the fall, and then in the spring you scored 83%. Well, you only went up 3%, right? So it's not really showing a lot of growth. Where someone else did 20%. That's a good point. And then in the fall they scored 40%. Well, they went up 20%. I'm okay with them going up 20%. They're going to get pretty much probably 100% of that portion of the growth measure for their final grade on their final. So your final, by the way, I might as well tell you, is going to be 50% your growth, and 50% is going to be that project on finals day. All right, so that's going to be your final. Why am I doing that? Why don't I just give you a final? Because you know what happens a week before your finals week, or 2 weeks before your finals week? Your end of course exams. The ones that you decide whether you part of the graduation points. Yeah. That's the big test. That's it. That's the big day. So there's 2 big days coming up, right? And they're right behind the other, like 2 months. And you know what? There's no reason to overly stress. Do you know all that work I've been giving you? Do you know all the lectures and all the videos and going over it and us reviewing? Guys, that's what the test is about. There's no reason to panic. Panic is not what I want. What I want you to do is be concerned, to put the effort in. Let me put it this way. You know, everybody here got 80% this last test, average 80%. So the people that do well, they know that they can, right? Well, let me tell you this. Last year, 9th graders, all 9th graders except one student got a 3 or above. 60% scored a 4 or 5, which is the highest you get. So, do you think that they're smarter than you? They're not. So I can't believe people didn't even answer that. This kind of scares me. They're not smarter than you. I know them, right? I've graded their tests. So I know they're not. I do you hear me? Because if anyone knows what's going on, I do. They're not smarter than you. So that means you can do this. So don't panic. Yeah.
Compared to previous years, are we in a position where the pattern is repeating for those?
Absolutely. You know what, guys? The kids from last year struggled just as much as you. In fact, you are benefiting from their struggles because a lot of the activities you've gotten, they've shown that they needed help with, and so I've given you some more support on it. The one thing that I am worried about is by this time last year, we were a little further ahead, but we've talked about why that is, and you hear me get stressed out and push you and go faster. But I also know last year some of the feedback was, look, I needed you to go a little this, and I needed you to do this and that and the other thing. And so that's what I've done this year, and that slowed us down. There's consequences to that, right? So there's consequences to trying to go back and go over this and go over that and do this again. So it slows us down a little bit. So yes, we are, for your end of course exam, we are fine. We're on track. For your ProCore, we were in the same boat last year, right? As far as not feeling like we had not finished, we didn't even finish ecology. When they took the ProCore last year, they didn't even do ecology. So you guys are, as far as comparing the year from year to year, you guys are on the same pace, all right? Now, some of them had a little bit more background in science than some of you, so that gave them a little bit of an advantage, but not a big one, all right? So I don't see any reason why you guys can't do as well, unless some of you start giving up. If some of you start giving up, and you don't start performing, start doing some work, I'll tell you this, you might think, some of those kids from last year might say, oh, well, we did this. There were more people this year that haven't been doing the work. That's true. That concerns me, all right? But last year, I know a lot of kids copied. But you know what happens when you copy the work? You copied it. You don't learn it as well as if you did it yourself, but at least you're familiar with it. When you don't turn it in at all, then you haven't even seen it, right? And then you're walking in on the test, and you're like, what was this? Also, last year, I had a lot more issues with behavior, but I also didn't have as many people falling asleep or not showing up. So do you see what I'm saying as far as give and take, right? Yeah.
So as long as you get a 3, you pass biology altogether?
No, your grade in this class does not depend on these tests, except for what I just showed you, right? With your ProCore. What I thought I explained this in detail. I did put it in the newsletter, but again, I don't know why people, your generation, I don't think reads unless you're forced to. But here's what I'm gonna say this. Am I right? Pretty much, right? So here's the thing. There's 2 parts to your graduating high school. There's the credits, your graduation credits. You need 20 some odd credits to graduate, and you need them dispersed in different categories. Those credits come from passing classes. So as long as you pass this class, you get your credits. You're on your way to graduate. You have to pass this class to graduate high school. Is that clear? Part of your credit is this ProCore exam. So you have to understand that. Is that clear? But this class is important for you to graduate high school. Here's another place where this class is important. A lot of you say you want to be doctors and nurses and go into the science field. Guess what you need to know? What this class teaches you, right? And some of you say, I don't want to go into the sciences. I want to be, well, you're going to have to take science in college anyways. Guess what science you're probably going to take? You're going to shoot chemistry or physics? Okay. You don't want to take science, but you're going to choose to take chemistry and physics. Okay. Oh, you were guessing. Okay. I thought you were being sarcastic. Well, no, because chemistry and physics is actually more intense, right? It's more, if you don't like science, there's a kind of a genre of people that don't like science. Those people that don't like science kind of steer away from chemistry and physics naturally. Does that make sense? Biology is at least related to what they experience in life, so they generally pick biology. Does that make sense? Now, some people might pick environmental science. That's another one that people are interested in. But environmental science, biology, that's where people kind of stick to. So when you go to college, you're probably going to want to take biology, so you're probably going to take this class again. So for all these reasons, this class is important. I've been trying to tell you that. I think you've heard these words before from me. Then, of course, you have your AP Biology option here in school. When you get up in your upper classes, AP Biology, AP Environmental Science, you have your connection to human body systems. As you can see, a lot of the same materials being covered in human body systems. You have to take human body systems next year, right? So all this stuff kind of compiles, and really, I encourage you to learn your material so that your life is easier in high school. The next 4 years, you're going to see the same ideas coming back to haunt you. Genetics, chi-square, DNA replication, protein synthesis. You'll see this at least 2 more times before you graduate high school, let alone in college. And if you're going to be a doctor and a nurse, you're going to see it the rest of your career. So take this stuff seriously. So that aside, though, you need to pass that end of course exam to get what are called graduation points. Now notice the words. One is credits, the other's points. Now Miss Simpson already talked to you about the points, right? Where you have to get the points, how many you have to get. You have to get 18. You only have so many chances. It turns out mathematically you need about a score of about an average of 3 on each test to graduate high school. But you need so many in science and social studies, another set in math. You need a minimum in each category. So it's not just 18. It's 18 exactly the way they want you to do it. So passing this end of course exam then becomes important for you for that reason as well. Getting a 3 on that test is going to make your life a lot easier. Scoring a 5 on that test, hello, happy days are here for you. Because that means less stress for you in chemistry or in social studies, in AP World History or whatever it is. Does that make sense? Because you need to get those, once you got those 18 points, then it's just you learning and preparing for college. So that's why I kept encouraging you, and still encourage you, focus on what I'm teaching you, what I teach you, what I test you on. And in fact, you know my tests, I'm telling you my tests are harder than the tests that you're going to take. My tests are harder. So you score 80% on these cladistics tests, I promise you the tests you see, the cladistics questions you get on the ProCore and the end of course exam are easier than the ones I give you. So you should feel confident, but not overconfident. Because if you don't study, you're not going to be able to do well either. So be consistent, a little every day, focus on what you have to focus on. Okay, so that's ProCore. That ProCore is happening again in 2 weeks. You have NWA next week. You got your graduation, your white coat ceremony this week. We have practice during advisory, so that means no advisory tutoring, no advisory retakes. I'd like some people to come after school and make sure they get their retakes and their remediation for any tests. I'd like you guys this week after school. I'm here every day after school this week. Please come and retake these tests. Please. All right? Now, does that settle everybody's questions with this work? Question? You had a question? Yes, go ahead. All right, so now let's look at some evolution. We're gonna, all right. I already went through that, and I will put it together for you next period. Now, have we started this yet?
No.
All right, so here we have agents of evolutionary change. And this is what drives evolution. When we're looking at evolution, and we haven't talked exactly what evolution is yet, you should have read the chapter by now. You should have done the homework and uploaded the homework. Yes, I know there's one assignment that doesn't have a slot in Jupyter grades, so that'll be due tomorrow, that one assignment, along with this package we just went over today will need to be uploaded tomorrow as well. So there are 5 things that drive evolution. We've already talked about at least 2 of them, really. We've talked about mutation in detail. You know what mutation is, you know it's random, you know it happens all the time, you know it can be influenced by chemicals and radiation. But you know it's so even though it's random, it happens consistently, and we can actually tell exactly, we can tell time with the number of mutations that happens in a species. So that's how constant mutations occur in nature. So mutations happen. Gene flow is when genes move from one area to another. How do genes move? What is the source of genes moving in a population?
Selection.
You know everything you need to know to answer this question. Mr. Tate, how do genes move from one population to another? If I have a bunch of bluebirds in one valley and I have yellow birds in another valley, how do genes move from one valley to the next valley? Mating. Genes move with sex. And yes, migration is an important part of that, isn't it? Because those bluebirds have to move over to the other valley in order to meet the yellow birds, right? How, as far as science is concerned, science doesn't care about it, the how matters to some extent. But the point is the genes move, right? The Moors were North African Muslims, and they moved from North Africa into Spain and controlled Spain for 500 years. They left their mosques and their Arabic architecture, Arabic language, what else did they leave behind in Spain? Genes. The two peoples are tightly connected because those genes came into an area for 500 years. So that influenced Spain for a long time. It's the truth with any population. I don't care if you're talking about humans or birds or worms. All these things, it's the same process, moving the genes from one population to the next. It influences that population moves on. You know that's true. You look like your parents. Some parts of you look like your parents. You may not, your biological parents have left a mark on you, have they not? You may not be your whole face, but some part of you. There's some part of you that is influenced by your biological parents. You know that, right? Both parents. So this should not be a shock. This should not be something you need to argue, right? So this is called gene flow. Gene flow is through migration, immigration or emigration. Emigration is by migration. Just say migration. Gene flow, the flow of genes, right, is migration. And then what? Mating. Successful mating. Successful mating. If you have only sterile individuals going into a population, then it doesn't matter. You have to be able to have babies for genes to flow, right? Genes have to flow. You have to have babies. You have to have, not just have sex, but have babies, and then those babies have the genes that become part of a population. This is an incredibly important point because this is what Hardy-Weinberg is all about. Hardy-Weinberg is it's not that hard if you get to know these little things. But the devil's in the detail. It's always the little things that people forget or didn't learn to begin with that makes the bigger things that much more difficult. So non-random mating. Non-random mating. This is going to be a double negative. This is a double negative. This is always hard in science. I don't like it. I wish we could get rid of it. Non-random mating is an evolutionary actor. We're looking at players, right? This is a play, and the play is called evolution. One actor is mutation. Another character is gene flow. Another agent, right? Another character, another actor is gene flow. The movement of genes from one population to another, for whatever reason. Yet one more actor is this idea of non-random mating. What does it mean, non-random mating? Help me. Help me understand what it means.
Doesn't it mates like with something else?
It does. Most things mate with other things, although there are some species of plants and animals that mate with themselves. But most things mate with other things. So that's true. So you're but is it random? What does it mean, non-random? Non means not. Go ahead.
No, I got that.
It is as easy as you think. It is the fact. Okay, it's not random. Okay, I got that.
So like, is
But
it
what-
something with the traits?
So say again.
Is it something that's closely related to them?
Okay, that's an interesting idea. So you're saying the things that mate that are closely related to one another. That could be, but something more general.
It's like their traits? Is this like,
Say-
they traits, like it's not.
They. What about the
they
traits?
show- It's not, they don't show like their,
The traits of recessive, something like that.
No, that's interesting too. But no.
I wanna say like, okay.
So mating is choosing to have sex with someone, having sex with something, right?
Oh,
They're not from the same area.
No, they could be from the same area.
They traits don't show as they would like,
No, they're not. It's not about showing or not showing.
The tiger and the lion.
I don't know.
Do I did not know
Say again. Say it. Say your thought. And this is all open. It's free. This is a chance for you to say something, to participate, and not get consequences instead of sitting there quietly, uncomfortably on a stool, and not really thinking about, not really wanting to think, and not saying anything. This is a chance for you to say something. Say it. Say something.
They both have one of those traits.
Oh,
So
it
like
says
they know the specific
it
outcome.
says the traits do not pass as quickly to the rest of the population.
Nope. Non-random mating.
Oh.
Non-random.
They know it.
They have sex is correct. They're gonna have sex. They're gonna have babies. They're gonna have sex and babies, right? We got that part. Let's put our ideas down. Non-random mating. Let's write them down. Let's see if we can figure this out without Mr. Mendoza having to tell you, right? Okay, keep that in mind. All right. So the answers I've heard is, what was the other day? So there's sex involved. That's true. There are babies, right? Let's say progeny. Can we say progeny? There's progeny, that's right? So we know that's true. Okay.
In this, in the ebook, it say new traits do not pass as quickly as the rest of the population.
Okay, that's a consequence of non-random mating, but you don't even understand what non-random mating is yet. So I'm asking you to tell me what non-random mating is. They choose. There's a choice. We call it.
So we have non-random sex, maybe.
Oh, that's so
Selection.
females don't look like the males.
That is right. That's part of it. It's sexual selection, where the males or females choose.
So you
There's a choice, and someone just said it.
Choice of who they have sex with?
Yeah. Is that strange to you?
I mean, of course you choose, but like.
Yeah, they have a choice. Let me tell you a story. I'm gonna tell you a story about sexual selection. And it's one of the reasons I didn't have the video out to you yet, because I wanted to include this little video or pictures in the video. Give me a second. I want to show you a movie as well. So, birds, can I ask you something? You've seen a peacock, right?
Yeah.
Why are the males so colorful?
So they try to
So they attract the females.
They attract the females, so that's not so animals do have a choice. Because the more colorful bird is the bird that the female chooses.
Yeah.
Often we think of, as humans, we think colorful, colorful. Someone's colorful, you think it's the female.
So is that the
Right.
same thing with like roosters and chickens?
It's the same with a lot of birds. And yes, you're right. The male roosters tend to have the bigger feathers and the really colorful color. That's what happens.
So am I the
So,
female peacock?
so there's a bird that, where the female, the bird is, I'm not sure what the name of the bird is, but there's a bird where the female chooses only the birds that make a nest for her with blue in it. If the nest doesn't have enough blue, then the female doesn't choose, right? Select that male. So these male birds go and get blue things anywhere they can get them. You better not have a blue sapphire ring laying about, because this male's gonna steal it. The more blue and shiny it is, the more likely this bird is gonna go get it.
That's a peacock.
No, it's not a peacock. It's just a bird. I don't remember the name of it.
Wait, that's a
It was
I'll
a
look
bird
at
at
it.
my house.
Okay, guys, you just keep getting out. That's not the point. Wow.
I'm asking, is that a feather in his mouth?
Right. I'm trying to say I'm trying to tell you, but could you just stop with the giggling and the talking and the talk? Okay, I'll wait. I'm not going to get upset, but I'm going to wait. So this is not a feather in its mouth. What this is guys, if you could just let me talk, it would really be nice if you just let me talk. So what this is a blue bottle cap and blue straws. And anything blue, if it's blue, if you leave a blue scarf around, it's gonna go get that blue scarf, blue yarn, a blue ribbon. This bird is gonna go and get it, and it produces these fantastic
That's so cute.
nests, these incredible architectural nests for the female. And this particular bird went and got these balls, these tennis balls, and poked holes in them and lit and put down this little, I don't know, what would you call that?
Those are shells.
They're not shells. These are tennis balls. All right. Look at the blue. This is the female. The female's inspecting it, deciding, is this guy good enough for me? Is this nest nice enough? Look at the nest that they built.
That is so pretty.
And the male goes and brings these piles of gifts for the female, right? Even dollar bills. Don't leave it. If it's blue, guess what they're doing? They're taking it. It's a $10 bill that this bird went and found out. It probably might have picked it out of somebody's wallet. Look, there's pencils. There's a blue toothbrush. If it's blue, it's bringing it.
How long you think it takes to make that nest?
A long time. Days.
Right. Like if you go in there like a
Here, these are piles. These aren't made by humans. These are made by birds. A male bird. I'll tell you later. I'm not going to
They make
spend.
the tree stick.
Everybody misses the big peep. God,
Right.
man.
We talk about the blue stuff. Y'all want to talk about?
You guys keep trying to get off of. You keep trying to get off off task. I'm trying to keep you on task. I'm asking you to get the point here. Yes, go ahead. You're not going to listen to me.
I'm still kind of confused. It's like, so if they see a blue straw or something, they gonna think that's from a male bird?
No.
No, the bird.
I'll say this again. I wish you'd listen, guys. Listen carefully to what I'm saying. Just listen. This male bird has to find blue things to bring and decorate the nest with. It's the only way he's going to get the female to choose him.
So they put it by the nest.
So they build this amazing nest that you just saw, and then they go out and look for blue things, blue flowers. There's a contest. That's what I'm trying to say to you. Is it's a contest. Males are competing with each other to try to attract the female. The ones that succeed get to have babies.
Suppose the male makes his nest and then the female comes and decides that he's the right guy, but does he decide if he wants her or not?
Now, he's attracting the female. He's attracting. I don't know what the details are. I don't know if the male then chooses which female. If more than one female shows up, does he choose which one? I don't know. All I know is that they build this nest and they bring these blue ribbons, these blue straws, these blue pens, blue anything that's blue, and they litter the nest with it, and they try to track. They're competing for a female's attention because they have to show that they are whatever. They can produce, they're healthy enough. Now, if you think about it, that bird that made that nest that you saw in a second ago on the screen, that bird has to be healthy, doesn't it? Because as someone just said, it took them a lot of work. So to build a nest like that takes a lot of work. So if they're able to do that work, if they're able to tell the difference between blue and some other color, if they're able to go and collect these things and not get caught, that means they're fast, right? If they're able to get a $10 bill away from you, they got to be fast, right? So the fact that they can build these nests is proof to the female that they're healthy, that they're worthy. Does that make sense? This is what the female has to decide in all of nature. In species where females choose, which is almost everywhere in the animal kingdom, the places where females choose, the females have to choose a male that has the genes that are going to get their kids to survive, right? Why do you want to have kids that are just going to die? That's not if you had a choice, you'd pick kids. You'd pick to have kids with someone who's going to give you healthy babies. This is nature, yes? This is why when two male sea lions fight, the strongest male gets to choose the females. That is the one that gets to have babies with the females. Does that make sense? This is why lions battle each other for control of the pride every 2 years, because only the strongest males get to have babies.
Oh, like Lion King?
Exactly like Lion King. Lion King is based on reality. The reality is that lions battle for control of the pride every 2 or 3 years.
Yep.
And the weaker lion dies or walks away, and the stronger lion takes over the pride and has cubs. Only the strong lions have cubs. Why? Because it guarantees the survival of the species. Healthy, young means those are the genes that go on. The birds that didn't make the blue nest, that didn't attract the female, don't get to have babies. Their genes are not in the next generation. Why does it have to be whistling? Yeah.
Okay, so they attract, like the birds. So they attract other birds that's not like them.
I don't understand your question.
Okay, so I'm saying it's all types of birds, right? So they look for any type of bird, like any type of female.
I would expect that they're trying to attract a female of their own species, right? And who's going to be attracted to this nest? Only those female birds that have genetically evolved to be attracted to blue nests, right?
What about a blue that's like already blue?
Wow. Okay. We're just going way off. Again, this is just one of those things. We're just gonna keep going off on tangents in every direction. I can't have this. So it's an interesting question that has nothing to do with the nest, the blue nest. Okay. But this example is exemplified by this peacock. Do you see the peacock, the non-random mating? Why would this peacock have this amazingly big, colorful set of feathers on its tail? It doesn't allow it to fly better. Attract the female. Well, the female chooses a bird that has what does this prove? That he has these beautiful big feathers. He's healthy.
Right.
He eats
Wow, that's
well. He's healthy. This guy can make me some babies that can survive. If I pick a male bird that doesn't have this color, I'm not so sure he's going to be able to survive.
this. Mr.
Yeah,
You know what your phone number is?
374. So that's the idea of non-random mating. In other words, we call it sexual selection. Humans do this. Human females choose males. We don't. Hold on a second. I'm gonna have to move some other people too, because this is not gonna continue. I can't. So human females choose as well, don't they? And there's kind of a style of people they choose. And if you look at the people that females choose, they generally choose healthy people. And there's different strategies. Some females will choose Males that are good homekeepers, that are good providers, right? You've heard that before. He's a good provider, right? You've heard that? Yes, no? That's old school thinking, but still, it's something that's something to consider, isn't it?
Bring something to the table.
It's bringing something to the table. What's this person bringing to the table? If I'm going to be with this person the rest of my life, or at least for a long time, and I'm going to have babies with this person, which is going to mean I got to deal with this person the rest of my life, right? If this person's the father of my babies, I got to choose someone I'm going to have to deal with the rest of my life. I got to think about this. Now, we as people, as human beings in our culture, we allow television and media to kind of drive who we choose, and then we get caught up in the moment and things like that. But in general, when you're making choices, these are kinds of things that go on through a person's mind. And the same thing with the male, right? So males and females, we're a lot more complicated than your average peacock. But with the sexual selection is still an issue, is my point, right? We are selecting who we choose to have babies with. Is that clear? So sexual selection does drive evolution. If human females started choosing only tall people to have children with, what's going to happen to the population of humans in a couple hundred years or 1,000 years? Our population is going to get taller.
That would be nice though.
Maybe, maybe not. Because maybe tall people then don't survive later because of it or something. Who knows? I don't know. You can't tell what's good or bad. All you know is what's good right then. All you know is what's working now. You don't know what's going to work next year or 100 years from now. All right, so that's sexual selection. Then you have that non-random mating. It's called non-random mating. Wow. The level of distraction in this class. You know what? Obviously I can't publish this, but I'm going to save this. I'm going to put it aside. I can't wait to have some conferences with some parents and say, let me play something for you. Genetic drift. Genetic drift is an idea that was going to take some time to develop, but it's an idea like, okay, so let me use this class as an example. Genetic drift is generally random, and let's assume that we are all living on one island, okay? Yep. And this is all the humans. We're one of the first. You know, Adam and Eve were our grandparents, and this is it. We're the kids, right? Just using an example. So we're hanging out. We got some genetic variation here, don't we?
Yeah.
All right. So you don't think there's genetic variation in the room? There is. There's a lot of genetic variation in the room. Shh. Thank you. So now let's say that let's count. What can we use? What trait should we use? Tall, short? What do you think? Tall and short?
Skin color.
I think you should use
We could use skin color. It is. Let's use skin color. It's the easiest one. I don't like to because it puts people on the spot. But it's the easiest one to identify. So let's go ahead and just use skin. So let's say. No, you know what? It's going to get uncomfortable if we start to use that.
Oh my gosh.
It's just hair color.
Hair color. All right.
Same thing. Get my hair dark. Pull over glasses.
Yeah,
Oh, okay, that's a good one. That's a good one. Okay, yeah, I like that. That's safe, right? All right, so let's use glasses or not glasses. So there's a gene that those of us that wear glasses, right? There's a gene that makes our eyes weaker than the rest of the group. Is this class over?
No.
What time is it?
It's only 44.
Why are there so many people wrong with it? Oh, okay. So there's those of us that, how many people in here wear glasses? Raise your hand. That's me. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 out of 30. Somebody with a calculator divide 14 out of 30, please. All right, 15 out of 30. So that's easy. That's half. Don't worry. We got it. Wow. It's okay. Wow. You can't do anything with this class without distraction. 15 out of 30 is half. So half of us wear glasses, right? Now we're all mingling around. Abbas, let's get up. Get up. Let's all stand up. Put you on your pencils and pens, and let's all get up.
Yeah, let's get up.
Miss Moore, stand up, please. Miss Moore, go ahead and stand up, please, quickly. I don't have time for this, to have a discussion with you. Let's get up. Let's start moving around, mingling. Let's go, mingle. We're going to do your life. We're gonna talk. We gotta go. Abbas, why don't you come over here? Come here. We're in the middle of the lab. This is a lab. Deal with it. It's a lab. Shut your mouth. Okay. Natural selection is about to happen. Just an event, some catastrophe. There's an earthquake, a volcano. This group right here, they're dead. Leave. Go to the doorway. You're all dead. Tay, you're dead too. Go to the door. All of you are dead. Not you. You're not dead. You're not dead. You survived. Go to the doorway. You're dead. Go. You're dead, man. Die already, Tay. You're not over here, bro. You're not over here. You're over there. Just go. We survived. No. This group survived. There's an earthquake. The earth opened up. Hey, why? It just happened. Let's go over here. We survived. You're dead, man. Go. You're gone. You shouldn't even be talking. All right. We're separated. There's a big ocean now in between us. Everybody else, this could be miles, right? Obviously, we could jump over this, or some of you can jump over there. Us can get a little boat. But this could be miles, right? We created whole oceans. You heard of Pangea, right? The Earth moves around. Stay over here. So now we had half the population need. So the half the population had the genes for the required glasses, right? But now we have two populations. We used to have one. Now we have two, don't we? Yep. We lost some. Poor kids. They're dead. But now, what is the frequency? Shh. Wait. You were trying, but you didn't make it. So over here, how many people wear glasses over here now in this population? 1, 2, 3, 4, 5, 6. Out of how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 6 out of 15, which is, wow, we're just going to talk no matter what, huh? You don't really care about learning, you're just here to just socialize. 16 out of, or 6 out of 16. Less than half, right? Less than half, do you agree? Yes. All right, it used to be 50%, now it's a lot less than 50, or less than 50%. Let's count over here. How many people have glasses? Need glasses? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 9 out of 12. Most of us need glasses.
Wow. 9 of us are wearing glasses over here.
Wow, it's impossible for you to focus on the main idea. Is that what I'm hearing from you? I want you to focus on the main idea. Who cares? Listen, who cares? So over here, we had 9 out of, what did I say? 9 out of 12 over here. We're 6 out of 16 over there. Fast forward several hundred years, which group of individuals are there going to be more people with glasses? This population. Over there, you're still gonna have some people. You're still gonna have some people with glasses, but it's really not that far off what it used to be, is it? Right. This population is gonna be mostly people with glasses. In fact, given the right circumstances, maybe only people with glasses over here. Yay. You know? All right, go ahead and take a seat. Thank you for working with me.
Thanks for that.
So that's called that idea that something could happen randomly. Miss Shepherd, can we get off there and listen? That idea that we could oh Lord, everything takes like 15 minutes to get done.
We got 7 minutes.
So that idea that randomly we can. That idea that something can happen, an earthquake, a volcano, something, I think there's a movie coming out, Jurassic Park World or something, where there's a big volcano that's gonna erupt, right? So there's these events that happen in nature, right? A hurricane, an earthquake, a rift in the land, the ocean floods a valley. Who knows, right? Something happens in nature that separates groups of individuals. And what happens when they get separated is they used to be what? They used to be about 50 in this case, red and yellow, right? Now this population is what? All red. So this population over time is going to have just red genes. This population is going to have both sets of genes. And that's what we see. This is called genetic drift. Random events that separate populations and over time increases the likelihood that you're going to get a different species, right? It could take a very long time for there to be a different species because it all depends what happens in the DNA and the changes in their structure and etc. But that's how you get different species. You get a separation of space or time, right? That doesn't allow the genes to flow, right? The genes can't flow here. In this case, maybe it was a hurricane that blew this little group of red birds onto an island that's too far for them to fly normally. So they can't fly back and forth. If they can't fly back and forth, then they're going to be separated. And if they're separated, then the populations can evolve separately. And that's how you get evolution occurring. This change in gene frequency over time. Remember, that's what evolution is a change in the gene frequency.
Wait,
Yeah.
that's what happened when, like in history, you hear about the people from all the other countries moving over here.
Yeah, that happens, but remember, we're not a different species, right? But it does populate, we did have evolution happen among humans. For hundreds of years, we had different separate populations. We had people in Africa, we had people in Europe, we had people here in North America. That wasn't always the case, right? Since all people came from Africa originally, coming from East Africa and walking up land bridges or what have you. You have Asians that separated for a long time, so you see different features, different characters in these populations, don't you? And that's because they were isolated geographically from one another. But we weren't completely isolated because we have people like Marco Polo who kept going back and forth and trading, right? So that still was occurring. It just wasn't happening often. Native Americans were completely isolated for a very long time until Columbus sailed the ocean blue in 1492. Miss Moore, would you please collect your things and move back there on that bench back there, please? Thank you. I got no other place to put you, dear. I apologize. So when we're dealing with this idea of separating populations, yes, it does have with the humans too. In fact, when the Europeans first got here, they brought diseases with them that they carried. They were immune to the diseases because they had genetic changes in their immune system that allowed them to deal with smallpox. Yes, people died of smallpox, but most people survived because of those genetic changes, the changes that occurred because of the mass deaths that happened in their history. There's a Black Plague and all these diseases that Europeans had to deal with. When they came over here to America, these Native Americans never dealt with those. Their population evolved without having to deal with. There were millions of Native Americans here when the Europeans landed. The smallpox epidemic wiped them out. Not completely, obviously, because they're still Native Americans to this day, but it brought their populations down significantly. It changed, and of course, what happened once the Europeans got here? What did the Europeans do with Native Americans? Well, yes, they did kill them in war. Yeah. What else happened?
Rape.
Which means what? Babies. Whether it be rape or consensual, the point is you have babies. You had gene flow. So once the Europeans came over, there was gene flow, and then there was this. What happened with gene flow and with mutations coming in and what you ended up, and sexual selection, what ended up happening is what? In natural selection, you had, by the way, the diseases coming over, that was called natural selection. And what happens then is what? Evolution. So the people here in America are not, African Americans are genetically different from the population of Africans in Africa, aren't they? Because genetically, historically, the populations have more European genes, if they've been here for many generations, than people in Africa. The same thing with Europeans, people of European ancestry that have been here. Their genes are significantly different from those people from Europe, right? Because they've had babies, and even though, I don't care who you are, you just can't control the genes in that other person that you meet, right? You're just looking at traits. You can't tell the genes that individual has. So there's this mix. There's this genetic. There's this gene flow that's happened that's changed this population. We call that evolution. Evolution does not just mean a new species. And when a new species evolves, we call it speciation. Evolution is just the change in gene frequency. Is that clear? You need to write that down and make sure you know it.
Say it again.
The evolution is just the change in gene frequency. Just like in the little lab that we just did, this little demo we just did, where we saw what happened, right? Something happens, whatever the case may be, there's 100 million different ways it can happen. But you change who survives and who doesn't, who has babies and who doesn't. It's just that simple. The last agent, the last actor that we have to worry about, and then we can go, is natural selection. I mentioned it a second ago with disease in Native Americans. Natural selection is just this idea the bird is choosing which ones?
The one that's not in the same color.
The one that's not green, right? So anything that's not green is going to get chosen by the bird first. That makes sense. It's the one that can see easier.
Right.
It's right.
The eagles get the rabbits.
That's right. That's how eagles get white rabbits in the green. Because you see green, they see a white rabbit moving, boom, dinner.
That was a problem on the one at Homework. It was a rabbit.
That's right. So that's it. Natural selection is this idea that nature selects out certain characters, and that's going to change the gene frequency, isn't it? Because here you have genes for blue. If you take out all the blue ones, you're changing how many blue genes are in this population. There used to be 2 out of 1, 2, 3, 4, 5, 6, 7, 2 out of 7. Now there's 1 out of 6. That's a difference. Does that make sense?
Yes.
All right, we'll talk more about this yesterday. Mostly good day today. Please try to keep on task. Thank you very much. Let's try to keep these seats permanent until we can figure out what's going on. Populations and gene pools, concepts. A population is a localized group of interbreeding individuals. So let's be clear what I mean by population. Let's make sure we know what that word means. A population is not race. Race is not a real thing that is defined in nature. Race is something we define as a social group. White, black, Hispanic, that's something we all say because it helps us understand Asians, Middle Easterns. This is stuff we say to help us group people. That's not nature. Populations are nature. So populations are a localized group, and that group could be Americans, could be United States of America, could be a population. It could be Cleveland. It can be your neighborhood. It could be anything, right? It could be a group of squirrels in your neighborhood. They are a population. All right, so population is a localized group, and of course, localized is very, 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 defined by circumstance. So what do we mean by local? Well, it depends on what scale are we talking about. When we talk about human and Neanderthal evolution, we talk about Africa. That's a big place. Or we talk about Europe. Relatively smaller than Africa, obviously, but still a big place. And we talk about the evolution of humans here in North America with Native Americans, or we talk about the evolution of camels, for instance. We have to talk about the entire world. Did you know, for instance, camels actually started in America? Did you know that camels evolved to walk on snow? That they use it to walk on sand today, but actually their feet are made to walk on snow.
Not sand.
Well, they use it now for sand, but it used to be snow. Isn't sand and snow very similar in the way it behaves, right? So it makes sense that they adapted over time to live in desert areas, but as they first started in northern areas and evolved to take advantage of their wide feet and walking on something like snow. So population is defined by the circumstance. How big an area's population all depends, or localized. Localized is defined by circumstance. So gene pool is a collection of alleles. So when we talk about a gene pool, when we need to start thinking. You need to start thinking. Anytime you have a population, you have a pool, like a pool of water. But instead of a pool of water, think of a pool of genes. So if we look at this group of people here, we have a certain set of genes. And that is our gene pool. And when I say genes, I mean, do you have the dominant or recessive of 10,000 different genes, right? And that what we have in this room is what we have. Maybe nobody has a recessive gene, a recessive version of this gene, right? So everybody's big A. So we only have big A's in this room, 100% big A. That's a gene pool. This is this gene pool. So you have to think about this when we move forward, because you're going to see there's going to be some tricky math that you're going to have to do with thinking about these genes and how many of these genes are in this population and how many these genes move. Allele frequency is how common is that allele in the population. So gene pool is how many you have in a specific how many genes, the genes that you have in a specific population, right? Allele frequency is how frequently do you find big A versus small a? Remember, alleles are what? The versions of those genes, right? Are we all good with this so far? A lot of this is review. That's why I'm going so quickly. Okay. What are populations? And evolution this is what evolution is. Everything else you ever heard of about, this is why evolution is less of a theory and pretty much accepted by anybody who has studied biology. I don't know of any biologist who says, evolution's not right, there's a big mistake. Let me pause this for a second. All right, evolution is pretty much accepted as a process of how populations change over time, because evolution's definition is really simple. It's a change in allele frequencies in a population. That's it. That's all evolution is. Of course, the consequences are big. What would determine if an allele frequency changes in a population? What determines that? Natural selection, that's right. A change in the environment. But why? How would that change? How does that impact the frequency of alleles? So let me give you an example. There's a gene that gives you 6 fingers. Did you know that? It's a recessive gene. Let's say in this room, 1/2 the people had the 6-finger gene. We all had, half of us had 6 fingers. The other had 5 fingers. There's no real advantage for 6 fingers, so nobody really worries about it. Today, a lot of the parents actually choose to have the 6-finger removed from children than have it before they're old enough to remember, surgery, not just cutting it off with a cigar cutter or something. So anyways, let me pause this for a second. So if something changed, and so all of a sudden having 6 fingers makes you more selective, interesting to the females in the population, right? Or 6 fingers makes you more capable of playing the piano, maybe, and that makes you more interesting to the girls, or maybe, or guys if you're a female, and maybe 6 fingers helps you pick up the stone faster, throw better. I don't know. 6 fingers all of a sudden gives you an advantage. You survive more, you collect more food, you can support more babies. So that's how sexual selection works, right? In the animal kingdom, those individuals that can provide sustenance, that can provide for a larger family, those are the ones that are chosen by the population, whether male or female. So what do you think is going to happen over time to the frequency of that allele?
It's gonna be more common.
It's going to become more common. Why?
Because more people will want it.
Because natural selection is going to choose it. It could be sexual selection, so more people want it, right? Or it could be natural. In other ways, it could be selected again, so you get positive selection, which is when it's chosen. Sexual selection chooses it. Sexual selection chooses it. Or it could be that nature decides, hey, anybody with 5 fingers that can't throw the rock right dies, right? Well, how could that happen? Maybe there's tigers that are chasing us, and the people that can throw the rock really well and hit the tiger on the nose, the tiger leaves you alone, you survive. But if you have 5 fingers, you can't throw the rock right, you miss the tiger that don't hit it hard enough, and the tiger doesn't go away and eats you. So the only ones left are the ones with 6 fingers. So, it's all kinds of crazy things happen. All right, non-evolving populations remove all agents of evolutionary change, and these are the 5 agents, right? If we remove all agents of evolutionary change, then theoretically what? If there's no mutations, there's no random mating, there's random mating, so there's no sexual selection, right? People meet and they either have babies or not, so there's no sexual selection. There's no, it's not just people, right? We're talking about animals. So if you're more comfortable talking about animals, go ahead. But it's all random mating. There's no mutation, so there's no gene flow, so there's nobody's coming in from the different population, nobody's going out. You have no natural selection. Everybody lives. We don't really have a lot of natural. So, can I just ask a question? Well, first let's say this. What does that mean for this population? No evolution. Our gene frequencies, the allele frequencies are going to stay the same. If we had 1/3 big A, 1/3 of us had big A, 2/3 of us had big B, 100% of us had big C, then that's how it's going to stay forever because none of these 5 things are happening. If you have one of these 5 things happening, then you're going to have a change in the allele frequency, right? But if you have none of these happening, then the allele frequency is going to stay the same for the rest of eternity, or however long it is until something changes. Is this possible? Is it possible to have all 5 not happen? Is there ever a time when we have no mutations? No, we can measure mutations. We use mutations as a clock. It's so predictable that that mutations are going to happen. We actually use it as a clock to measure how old a species is, right? We did that with our cladistics, didn't we? So we know that mutations happen regularly. So this is not even possible, right? Migration. Do things not migrate? Do people not move? They do. They move all the time. Do birds not fly from one place to the other? They do. It's not possible to keep everything contained. Even if, in some cases, we know that, for instance, you've heard of the Galapagos Islands. Do you know, you ever wonder how did lizards get out there? How'd you get a tortoise who can't swim? How'd you get it out to the...
Oh, ships.
They didn't walk. Huh? Some people took it. That's a possibility. So there's migration, maybe not by choice, but there's migration, right?
Or some animals mated. I don't know.
Right, it's hard, right, to think about how it might happen. Let me tell you what happened to someone in the Dominican Republic during a hurricane, and let me tell you that this happens all the time with people, with animals. So there was a hurricane in the Caribbean, and someone in the Dominican Republic, a woman with her baby, I think it was a baby, maybe she didn't have a baby, but I remember for some reason there was a baby. And the hurricane knocked her into the ocean, and she grabbed the tree and she held on. However much time it took, she ended up on the shores, holding onto the tree, on the shores of Florida, 300 miles away. So that happens to animals all the time, right? I mean, that could happen. There's a big hurricane or monsoon comes along, knocks them into the water, they grab onto something, hold on, and however long it takes for the currents to take them somewhere new, now all of a sudden they're on these islands. These lizards before were in Peru, and now they're on the Galapagos Islands. They have plenty of food, so now you have these lizards that are living on land. They're land creatures that cross thousands of miles of ocean, or maybe not thousands, but hundreds of miles of ocean, even though they can't swim. They didn't build the boat, they just held on to whatever they could find. Humans, we know, build boats, we move. That's what we do, right? We move we filled in every niche, every environment on the planet, right? So that's it. So this is also something that probably won't happen. No natural selection. It's hard to believe that the environment's not going to change in a way that's going to select that where you're not going to get the selection of one individual group of people over another. That's hard to think of a circumstance where that won't happen. Now, there's one key thing that we're not thinking about, and that's time. Time is a big factor here. For instance, in the time that we've been in this class, I know some of you might think we've been here forever, but for the time that we've been in this class, we have not evolved, have we? These 5 things have not happened in the however long we've been here, right? So in a short period of time, these 5 things can be true. Over a long period of time, it's impossible for these 5 things to be true. There will be movement of individuals in one. It just takes one person from somewhere else, or one animal from somewhere else to join a population. You have gene flow. Just one. So these 5 things over a long period of time are going to happen. There will be evolution. Evolution is inevitable. The question is, in the short term, does it happen? That is a question we have to consider. Apply this understanding of chi-squared to Hardy-Weinberg. We're going to look at the null hypothesis again. Well, Hardy and Weinberg, 2 different people. The mathematician was G.H. Hardy, and the physician, a doctor named W. Weinberg. I don't know why did it do that. Hold on, let me pause it. I think there's interference from somebody's iPhone or tablet or something. So anyways, hypothetically, he says, non-evolving populations preserve their allele frequency. Just like we said a minute ago with our example, if we didn't have these 5 things occurring here, within the time that we spent here, our allele frequency stayed the same. So if we have a population that's not evolving, then the allele frequency stays the same. Serves as a model for in other words, it's the null hypothesis. Remember we talked about the null hypothesis? The null hypothesis is that there is no evolution. That any differences that are happening here are random. There's no evolution happening. Any changes in the allele frequencies, it may not be exactly as predicted, but it's within tolerance of random events. So null hypothesis, it means that if you are not evolving, then you are accepted in the null hypothesis. Natural populations rarely find this equilibrium. This is called the Hardy-Weinberg equilibrium, where the allele frequencies don't change. And therefore there is no evolution. We call that the Hardy-Weinberg equilibrium. So you want me to write it down so we're all clear on what is important here? So the Hardy-Weinberg equilibrium is that no evolution is happening. That's number 1. And how do we know that? Well, number 2, the allele frequency does not change. Or rather, I should say, is not changing. And the third postulate, or idea that falls under the Hardy-Weinberg equilibrium, that means that none of the 5, and what are the 5 things? What are the 5 forces? Let's call them agents. Yeah, agents is a better word. Agents of evolution this is key, not happening. There's a lot of this stuff in science where it's like, this is not the case. This drives people crazy, right? When these 5 things are not happening, that's when you have Hardy-Weinberg equilibrium. When they're not happening, that's when you have Hardy-Weinberg equilibrium. So what are these 5 agents? None of the 5 agents of evolution are oh wait, I did a double negative, didn't I? This is when the 5 agents, when I put not, didn't I? Did you notice that? Nobody noticed that? I said none of the 5 agents of evolution are not happening. That's a double negative. That's ridiculous. So that means the positive, right? So the 5 agents of evolution are not happening. What are the 5 agents? We know what? Give me some. Mutations, genetic drift, gene flow, natural selection, and non-random mating. So if those 5 things are not happening, you see how confusing this can get? When non-random mating is not happening, what? So when there's random mating, right? So you have to be careful how you read this. Okay, so that's what Hardy-Weinberg equilibrium means. When we find populations that are in Hardy-Weinberg equilibrium, we accept what? The null hypothesis. So when we find the Hardy-Weinberg equilibrium, when we accept it, when we find that in our Hardy-Weinberg equilibrium, we're accepting the null hypothesis. We're saying there is no evolution.
So is the Hardy-Weinberg equilibrium, is that referring to the entire population or individuals for one period of time? Because you're talking about evolution doesn't happen in individuals, it happens in populations. So what is it addressing?
Perfect question. It is the population. We're talking about the opposite. So we're looking at a population.
So this is the opposite of what is usually believed.
What's that? Go ahead.
So evolution is, you said it was something that's basically considered true.
Yeah.
Except for this is saying it's not true.
Okay, good. Yeah, that's right.
Okay.
So what it's saying is that if this is true, if this is, we just said evolution did not happen since we walked in this class for the humans in this classroom. So it's all, whether evolution has occurred or not, it's about time. And that's that thing that's hard for humans to really think about. Because if you're talking about a short period of time, obviously humans haven't evolved. We haven't seen anybody with like X-ray vision yet, right? That's not going to happen. I don't know why I brought that up, but it's a point of contention. It doesn't. It's not possible. Well, maybe. I don't know. Whatever. It's just accept that that was a silly thing to say. So in any case, when we're talking about Hardy-Weinberg equilibrium, what we're talking about this idea that even though we know evolution occurs all the time because those 5 things that we just talked about happen.
So this is just referring to individuals, but not...
No, it's the population. We're just talking about a short period of time. If it's not been long enough.
Okay, so it's not saying that evolution doesn't exist. It's saying evolution doesn't happen in short periods of time.
It says that sometimes we can find situations in a short period of time where evolution didn't happen. You'll see more about what I mean. This is just a theory. We're going to look at the equation next, and we're going to look at how we find that out. And we're going to find numbers. There's actually we've actually put numbers to this, and you're going to have to do calculations and solve problems. So this is not just all theoretical, but this is the theory behind it. So we use this model to measure if forces are acting on a population or not. So if we're getting forces, if we know that how, not just if they're acting, but how much of an action is there? How big of evolutionary pressures are there on a population? Because populations change over time, but how much do they change? How big a gene frequency change do you see? And what will that result? And then fast forward that, what result will that lead to in 1,000 or 2,000 or a million years? So this is the theorem. And to start with the Hardy-Weinberg theorem, we have to start breaking down what alleles are, and then we have to start talking about frequencies. It's 2:11. I just want to get through this and talk about defining what P and Q are, And then the next slide, I'll just show you what the equation is, and then we'll end there, okay? What I'd like you to do, though, this weekend is to please focus on completing that the work that's due Tuesday, and your chapter reading that will talk about this. Your chapter reading is all about evolution, so read the chapter, complete the problem set. I think there's 3 assignments you have to do, or 4 assignments you have to do. Get that done, so when we discuss it all in class on Monday, everybody's caught up. Do you like this strategy? Anybody have any suggestions for making it better? If you do, just let me know. Email me you guys tell me all the time, so it doesn't matter. I'm confident that you'll let me know if you don't like something. All right. So counting alleles. Assume there's 2 alleles. There's just a big B and a little b. We know that there's more often, right? But let's just assume there's just 2. If we have the frequency of the big allele, big B, the dominant allele, the dominant version of the gene, we're going to call it P. So make sure you learn that, right? Because you're going to have to do calculations. You're going to have to start.
So dominant
Dominant's always going to be P. That's defined for us. We're going to call the recessive allele, we're going to call it Q. So P is the dominant frequency, not the allele itself, but the frequency. So if there's 25% of the alleles in this room are big B, then our P is equal to what?
Okay, so wait, can you reset?
So let me say this. If we have a population of cats, I'm just gonna, in a circle, a bunch of cats. And we say 25% of the cats have 25% of the genes, not the cats, the genes, are big B. Can I ask you, first of all, what is the rest? What is 75%? Little b, right? It's either big B or little b. There's only 2 options. So if 25% are big B, then what is this? Then what equals, what does P equal? 25% or 0.25, right? Do you realize that 25% is the same as 0.25?
Yes.
All right. It's just converting it. We just have to convert it.
So it's saying that even if the dominant, it's just whatever dominant in the population, not necessarily dominant or recessive in genetics. Does that make sense?
Yes. We're not talking about the phenotype. So that's really the key. Yeah, that's the thing, is you're not looking at this and saying that 25% of these cats are in this case what? I don't know, what do you call that? Black? Is that black? Yeah. Then we're not saying that 25% are black, right? What we're saying is that 25% of the genes are dominant genes. So what's the difference? Look at this. Look at carefully. This version of black cat has what? 2 big B's. This one only has 1. When we're talking about percent of genes, we're talking about all the genes in the population. So if you had 25 out of 100 cats were black, right? That would not mean that you have 25% of the genes are black, are big B, because some of those black cats might have a little b in them. So you have to consider that as you're moving forward. So you don't have to understand this 100% yet. We're not there yet, but just think about that. So those are good questions. Those are things you should be thinking about. All right, so now let's look at this second one. The frequency of the recessive, the little b, is Q. So if we said that what's really cool is if you know that 25% of the big B is big B, what do you know about about 75% is what? Little b. So Q is equal to what? 0.75. So that's really easy. That's what's great. And you'll see that that's one of the 2 equations. In fact, here's the equation. This is why this is true. Do you see why that's true? P plus Q is always equal to what? 1, 100%, or 1. Good. 100%. 1 is 100%, right? And 0.75 is 25%, 0.75 is 75%. Are we good with that? So really, that's the simplest form of this equation.